Hello everyone. So today I'm going to go through kind of a quick description of what you're going to be doing inside of the communications lab this week. What we're going to be trying to do is kind of walk you through the process of doing digital modulation using Matlab code. You can see from the description here that effectively what you're going to be doing is you're going to be generating modulated waveforms that are both that are ASK modulated, FSK modulated, and PSK modulated, and then measuring the spectrum. Or at least displaying the spectrum on a graph. So for the procedure, what it initially the laboratory manual provides you with this NRZ on-off signals generated using random bit sequences. And so it gives you kind of a description here, but it's actually also listed all the way down in the appendix at the bottom. So the first thing you want to do when you start this lab is to go ahead and copy all of this. This is lab8.m. and also this pulse encode.m. These are two separate files, so remember that. This is actually a function. So those of you that aren't familiar with Matlab, make sure that you save this as a .m separate from lab8.m, otherwise you won't be able to call this function inside of lab8. So lab8 does most of the grunt work for you. So what it does, it sets up your bit stream. It sets up the number of bits per waveform that you're sampling. It sets up the sampling rate. It sets up, it defines all of your arrays. It generates a random bit sequence, and it modulates a waveform. So where all the magic in this thing is occurring is basically inside of this for loop, which is, it says for m equals 1 to the larger m. This right here is your bit sequence, or B, and it's going to be a randomly generated value here. And you know, this basically just generates a sequence of ones and zeros, which is what you're looking for to do the modulation of. This right here is what actually is modulating your signal. So for all of the other items that you're going to be asked to build, you're going to be building them basically with this same framework. So I'm going to go over to Matlab now, and I'm going to show you lab8, lab8.m. So this is the same thing that was there just a moment ago, and except that now it's inside of the Matlab environment. And you notice that, you know, I didn't do anything special. Pulse encode is here, pulse encode is also here, and all I do is I'm going to go ahead and hit the run button. And when I do, I will generate this waveform. Okay, so this is the power spectra of an NRZ waveform. All right, and if, for those of you who aren't familiar or don't remember from class, NRZ stands for not returned to zero, which means that the sequence is oscillating between some positive and some negative value, and it's never returning to zero. Now, this is, you're going to be asked a question about what this is, so you're going to have to remember back to your lecture series on why you think you might have this line that's vertical right here on top of the primary peak for your output spectrum. Okay, so you know, go back into your notes, and I'm sure you'll be able to find something there. Now, the next part of the lab is going to ask you to do some special modifications. So I'm going to go back to here, and go back up to the lab here. And for ASK, what it wants you to do is to take a look at the pulse encode function, and to obtain the ASK, you need to come up with a change to either pulse encode or create your own function, whereby you're going to implement this function here instead of the way that the NRZ function handled it. And this is the suggestion for the function itself: the bit stream, the carrier frequency, the number of samples, and the sample frequency. Remember, FS is generated inside of that initial code, B is generated inside of that initial code, N is generated inside of that initial code. So the only thing that you should have to add to this particular sequence is your carrier frequency, or FC. Okay? And then it'll automatically calculate this for you. So I've done that in my editor under lab8 ASK, and you'll notice that I haven't even changed any of the comments. Basically, I just took the same thing here inside of this for loop that's doing all of the encoding, and I changed this from pulse encode, if you can see where my cursor is, to ASK. I left the bit stream intact. I set it to a carrier of 1 kilohertz. I left N intact, and then I changed the K to FS, or sample frequency, which is defined up here. Okay? So when I did that, and I come up with a plot that looks something like this. Right, so you can see that my carrier 1 kilohertz right here is where my waveform is coming from, and I have that broad peak, and I have another little line that's coming up off the top. Now, just to point out, this is kind of a hint for where NRZ is coming from. Okay, so just keep that in mind when you're going through and doing your lab. Now, I'm not going to show you how to do ASK. But think of it in the terms of that you just want, instead of with NRZ it was going from 0 to 1, what you want to do this time is to modulate the signal onto a carrier and then set the amplitude of that carrier to both a 0 and a 1, except in this case it's going to be two separate levels. Okay, so that's why my waveform looks the way that it does. Now I can also go through and do the same thing for FSK. FSK is FSK of the bit stream. I put it at 2 kilohertz carrier. N and frequency of the sample, and then 500. What this is actually the delta F that you're going to add to your total modulation. You can play around with these numbers. I just kind of selected these at random, but if you do it correctly, you should come out with something that looks something like this. Though it may look radically different depending upon how much you modulate your signal. As a matter of fact, if I change this to another number, let's say 100, which is lower, and I rerun this, you'll notice that it changes a bit there. I could also increase it quite a bit and put it up to 1,000. And now you'll notice something too, that this one kind of looks like our PSK modulation, but you'd have to do the full calculation to figure out where it's coming from. Let's try messing around with this a little bit. 500. There you go. And you can see that you can make it do a lot of different things based off of what you set your carrier to and what you set your deviation of your signal to as a percentage. Remember, it has to do with beta, right? So it's how much modulation due to whatever your message signal is. Now, if I go to PSK, I did, again, basically the same thing. And this comes out of the laboratory experiment here. Where PSK and FSK, it tells you basically to do, take what you did with ASK, except now what you're going to do is, instead of changing the amplitude, you're going to change the phase of the signal, or you're going to change the frequency of the signal. So if I set the carrier frequency to, what did it say for? So 10 kilohertz is the carrier frequency. So I'll go ahead and modify those inside of the code. I didn't actually do that earlier. So under FSK, I'm going to put this to 10K. Yeah, 10K. And then it wants my deviation to be 2K, because that's what it called out in the delta F should be 2K. And this is my waveform for my FSK. If I go to my PSK and I do the same thing, using the same carrier, I get this waveform here. So either way, I know this is kind of fairly short here, but remember, all you're going to be doing is basically modifying this pulse encode function to do these, the FSK, the PSK, or the ASK modulation. It's relatively straightforward if you just follow what your notes about these types of modulations entail. And again, most of the heavy lifting has been done for you already inside of this lab 8.m. So the only thing that should be, the only thing you really have to contemplate here is how to make it go from ASK to FSK to PSK. All right? So I believe that is going to be it for now.